So first of all, let's say I couldn't come here last year, and it's thanks to the help of the LLVM organizers that I was able to come this year, so that was very kind of them. And they even let me give a talk, in spite of the fact I warned them that I like to talk on and go way over time, but Bill here is apparently authorized to stop me with extreme prejudice. All right. So I'm going to be talking about the plugin project, which is basically porting LLVM-gcc to GCC 4.5, which is like the latest version, and completely redesigning it using plugin architecture. Let me first explain a bit what LLVM-gcc is. So this was historically the main front end to LLVM. And probably it's going to continue to be the main front end for a little bit because it's the only one that can compile C++, serious C++ for the moment. It's a drop-in replacement for GCC, takes all the same command line arguments, works in exactly the same way, and that's because it actually is GCC. To be more precise, it's Apple's version of GCC 4.2, and it's been modified. The basic principle is to rip out all the GCC optimizers, replace them with LLVM's optimizers, rip out GCC codegen, replace that with LLVM code generators. Let me just say a word about this version of GCC. I mean, internally, GCC 4.2, it's like the Stone Age compared to modern GCC architecture. But Apple has been works a lot on this. They've implemented many interesting features. For example, features which have been implemented in more recent GCC, for example, C99 inline semantics. Doesn't exist in mainline GCC 4.2, but Apple has it. They've got a lot of interesting features. It's highly worked on. So from the GCC perspective, 4.2 sounds quite old, but this Apple GCC, it's actually is not an outdated compiler in any way. Okay. And anyway, to achieve this replacement of GCC's optimizers and code gen with LLVMs, there are about 300 modified files inside GCC here. Now, I think this is an overestimate because I checked some and they were clearly actually Apple modifications which got tagged as LLVM modifications. But actually, there's quite a lot of places that got changed inside GCC to do this. And it's licensed under the GPL version 2 or later, same as GCC 4.2. Let me give a kind of conceptual overview of how it works. GCC front ends, you've got a bunch of different languages. They do whatever they like with your input file, but eventually they have to squirt out GCC's intermediate representation, which is called GIMPL. That stands for GNU Simple. And then the GCC high-level optimizers work on that. These should really be called GIMPL optimizers, but because these things used to be a thing called a tree, they're just called tree optimizers. And then this GIMPL is converted to a different representation called register transfer language, which is much closer to the target machine. This is now a preparation for generating final code. There's a whole bunch of optimizers that work on that. And then assembler is squirted out. And in LLVM-gcc, what's happened is that instead of this GIMPL is first converted to LLVM's IR, which I'm just going to refer to as bitcode, because there are too many different IRs floating around here, so I'll just call it bitcode.
5-second break here.
Yeah, I hope you're taking into account to get extra time for this. Okay.
Much better.
Thanks. All right. And once you've got it into LLVM's intermediate representation, you run the LLVMs, high-level optimizers, which are kind of analog here. There's actually a red cross that turned up here, but I only discovered when projecting that it's like way too thin. So this guy goes away. And then actually, at this point, there's an option where you can just squirt this out to a file for example, for doing later link time optimization. But if you continue on to generate machine code, then at this point you also, LLVM has a lower level representation close to the target machine called selection DAG. It's got its own optimizers. They're kind of the analog of RTL optimizers. And then you squirt out your final target assembler. So this is kind of conceptual picture of what happened. This is ripped out, replaced with LLVM's version. Though this is actually not really how it happens. This is actually how it's going to happen pretty much in the plugin, which I'm going to describe in a moment. What really happens is there should be some sort of line from sort of here over here, because the strategy in LLVM-gcc is every time GCC converts something to RTL, that place has been modified so that you convert to LLVM's bitcode instead. So you've got a global variable, rather than attaching some RTL to it, you attach some bitcode to it at the same place. So all kinds of different places in GCC that do this kind of thing had to be modified to turn it into LLVM's bitcode instead. Okay. Now, there may be some space aliens in the audience here who just arrived from another planet. So let me quickly tell those people who don't know what GCC is a little bit about it. So it's a widely used open source compiler that can compile very widely used languages like Ada and Fortran. And it can even compile things like C and C++, which I understand some people are interested in. Also Java and Objective-C, Objective-C++. Okay. And it's currently version 4.5 is being worked on. It will probably be released at the end of next year. That's just an estimate. And compared to GCC 4.2, which is what LLVM-gcc is based on, it's had about 3 years' worth of development. And during those 3 years, there have been a lot of changes, sort of user-visible changes. Of course, it shouldn't spit on the fact that they fix a lot of bugs. Okay, they probably introduced some too, but there's a lot of annoyances that have been fixed. Support for this C++, presumably X equals 9 here, but people tell me that it's not going to be ready this year. Support for newer standard. Lots of changes to the standard library to use these new features. Also, parallel versions of various algorithms and things like this. My main interest is in Ada. There's an Ada 2005 standard. The support in GCC 4.5 is way superior to GCC 4.2. This is why I'm interested in recent GCC. Fortran also got many major changes, also in code generation. OpenMP, this is for having things executed in parallel in a fairly automatic fashion. It's gone up to a more recent version. So there are many interesting features in recent GCC. Okay, so having explained LLVM, GCC, and GCC, what is this plugin thing? Well, it's physically, or I guess since it's in the computer, it's not very physical, it's just a shared library. Weighs in about 8 megabytes. You can just load it into GCC at runtime, GCC 4.5, because it's got this new plugin mechanism that allows you to load in things at runtime, and it just suddenly makes GCC 4.5 look and act just like LLVM-gcc. So let me show how it works. I was going to do this live, but I think it might take too long. So for example, here is GCC, hello.c, it's a hello world program. Tell this -s says spit out assembler, -o-, that's just spit it to standard output. A little bit of optimization so it's not too cruddy. If any of you are not allowed to have anything to do with GPL version 3, you have to close your eyes right now, okay? Because this is GPL version 3 program. Okay, so you can open them again now. And this is the result. It produces some assembler. Here in this ident string, you see that it was GCC 4.5, compiled a couple of days ago. And it's a hello world program. Now to use this plugin, you just have the same thing, and you just add in -f plugin, and you give the path to this shared library. And it was, well, it's sort of hello world, but now it was all done by LLVM. In this ident string, you see that LLVM was there, and this was optimized and code gen by the LLVM optimizers and code generators. And that's kind of the whole story. You don't need to modify GCC, you just load in a dynamic library. This plugin can also take options. This GCC plugin architecture has a way of specifying options -f plugin arg, the name of the plugin, and then whatever it is. So if I want to output directly LLVM bitcode, I just add this, and kaboom, there you are. So that's the concept. And it can compile hello world. Let's just say that this is a very recent project. I started it about 2 months ago. I then went on holiday, having said to the organizers I was going to talk about this, and I hadn't actually, the project didn't even exist. I then went on holiday for a couple of weeks and came back, so it's like, it's not that old at all. And even, I think 3 weeks ago, I triumphantly announced I could compile the empty function. But I can now compile GCC using it, for example, and it works. I can compile a lot of C. Okay. I can actually compile quite a lot of Fortran as well. You see, this plugin just works with any GCC language. Probably it works with Java too, but I couldn't actually get GCC to compile in Java itself without the plugin, so I don't know. I compile all of LARPAC. I didn't test whether it actually works, but it certainly just happily compiles it. It tends to fall over fairly quickly on C++, and that's because there's no support for exception handling. In the moment you've got destructors and things like that, because an exception might be unwinding, you have to have some kind of exception handling stuff, and it tends to sort of crash fairly soon. But if your C++ is simple enough, it certainly works, and probably I'll fix up exception handling any day now. And it falls over even faster on Adder, which is kind of a pity because that's what I'm interested in. It doesn't produce any debug info whatsoever. Well, I'm sure it's easily fixed. No support for exception handling. Currently, it only targets Intel processors. It would be very easy to add support for others, but I don't have access to any others, so I can't test anything, so someone else who's interested can maybe do that. It works on Linux. Anton managed to get it working on Darwin. In fact, GCC itself refuses to build with plugin support for Darwin because it tests to see whether Darwin supports shared libraries, and it concludes that it doesn't, because shared libraries is a little bit different on Darwin, and its test works on Linux, basically. But Anton managed to get it built, and apparently it worked. Okay, so now it can actually compile quite a lot of stuff. I mean, it's very early days. I did some benchmarks. Now, I'm a VI user, not an Emacs user, so I don't do graphs and things, right? I mean, I just do numbers. Okay, so I did some numbers. So this SQLite 3, I chose it because it's a very big, or fairly big, 85,000 line C source file of real code, not artificial code. I was most interested in compile time numbers. But I also did runtime numbers. So what you see is that if I compile this using the plugin or using LLVM-gcc, the runtime is just the same. This is at maximum optimization level, -03. Clang produces slightly slower code. They tell me that they haven't really worked too hard on producing, easily optimizable or quality code yet. GCC runs 13% faster. I guess the GCC people were doing something with the optimizers during all these years. Okay, well, that's nice. GCC does take 15.5 seconds to compile this, while Clang only takes a bit over 6 seconds. LLVM-gcc takes a little bit longer, and the plugin, it's a bit slower. There's no theoretical reason, I think, why it has to be slower. Currently, I didn't do any profiling or anything. And likewise, for memory, the big hog is GCC. Plugin, it's a bit more of a hog than LLVM-gcc. Clang, very nice. Much less memory than anyone else. Final executable, not sure why this is so much smaller. These are all stripped, but it's just a lot smaller. Bitcode is kind of comparable with LLVM-gcc. The bitcode sizes shouldn't be taken too seriously because they include debugging names that are used, so it's easy to read the bitcode and that have no effect on the final object code. But they tend to fatten up the bitcode a lot. So, for example, it's not clear whether this is because there's really more stuff in it, or it's just that they produce lots of helpful names for the developers. And these kind of results, which is basically runtime is kind of the same for the plugin llvm-gcc, but it's a bit slower and a bit fatter. Well, that's kind of the same in all optimization levels. So I did them all. I'll just mention -02. -02 is amusing because with GCC, it's still faster than all the others at -03 optimization level. But hey, that's life. But GCC compile time sort of dropped. And if you go all the way down to no optimization at all, it's always the same story. The plugin, a little bit slower, a little bit fatter, but fairly comparable to llvm-gcc. This plugin has a number of advantages. For example, you get all these great new front-end GCC features. For me, the much more powerful adder front-end. OpenMP. I think Chris told me they have no plans to support this in Clang. It's extremely easy to try. You've got your GCC. Well, of course, you have to have a very recent GCC. But if you've got it and you want to try this plugin, you just add this command line and go kaboom. That's it. You don't need to modify GCC at all. There's a star. If I knew how to do presentations, when I press this button, that star would turn up. Instead, I'll go down, and here's the star. There's only one patch, and that makes some functions declared static. It just removes the static keyword on 4 functions. Okay, I have a plan so that that won't be needed anymore, but I didn't have time to do it. In the long run, the aim is no GCC modifications required. You just specify the plugin on the command line, and away you go. Distributing LLVM-gcc, you're distributing an entire GCC distribution. They had to remove a bunch of Java files, for example, because it was just so fat. But here you've just got one 8 megabyte file. Okay, you just ship that. Why not? For comparing the latest optimizers, extremely convenient. You've got really identical input to the GCC and LLVM optimizers. So that's quite useful for understanding why one does better than the other. And for developing the plugin itself, it was quickly noticeable that it's much easier to do a kind of modify, compile, test cycle than in llvm-gcc, because you just have to rebuild this shared library, and that doesn't take very long. But you see, saying I have 10 minutes, but without a threat to back it up. You see, this is, geopolitics. You need to have a threat to back it up, otherwise I'll just ignore you. So, okay.
I'll throw my iPhone at you.
He'll throw. Okay, I always wanted an iPhone. The plugin has a bunch of disadvantages. It's not mature. It's a very recent project. There's no reason why it shouldn't become very solid, but it does occasionally crash. What can you expect? It is slower. It does use more memory. I think I can overcome all this, but I didn't do it yet, so that's just a guess. Maybe GCC itself, 4.5, is kind of slow and fat. I don't think it is. In LLVM-gcc, you get to benefit from all these great Apple features they added in. For example, this blocks extension. There's some talk about adding this to GCC, but it's not there yet. So if you want it, you're not going to get it by going by GCC 4.5. You've got these really horrible command line options. They're very long. This is what is in LLVM-gcc. I guess there could be some wrapper script that just takes care of all this kind of stuff, but, And GCC 4.5 is licensed under version 3 of the GPL. Now, the plugin code itself is under version 2 or later, but the moment you kind of sort of compile it, I think you're getting a combined work, and it's pretty clear that this plugin is under the GPL version 3, and some companies have a problem with that. Okay, so this could be fatal for some people. All right, so let me explain a little bit how this plugin works. Well, the plugin architecture is pretty straightforward. When GCC starts up, whatever language front end you have, so it does some very early initialization, and then it immediately loads a plugin if one was specified on the command line. And it calls this predefined function, which every plugin has to define, plugin init. And at that point, the plugin is responsible for registering callbacks with GCC. It can register callbacks for various events, which I'll show you in a second. And one other thing it can do is it can add new optimization passes. These optimization passes can simply be in addition to the existing ones, or they can replace an existing optimization pass. So the plugin, it passes its own plugin arguments, registers a bunch of callbacks, and it does register some passes. It turns off all the GCC optimizations by the simple trick of registering a pass that does nothing and saying, please replace the GCC pass with this one. So it has a list. This is a bit fragile having this list, but it has a list of all GCC optimization passes, and each one it says, place my do nothing pass on top of this one. And that turns off all GCC optimizations. And GCC does code generation for functions also as a pass. And so the plugin simply says, please replace that with a new wonder pass, which just converts Gimple to bitcode. So at this point, it's registered all these new passes. Control goes back to GCC. At this point, only GCC passes its own options. So if you're interested in intercepting them and modifying the plugin based on those, you have to do it later. At this point, you're about to start processing a compilation unit. If you register the plugin, which we did, a callback, which we did, callback is called. Plugin uses this. For example, if you specified you want to do link time optimization, it's a new GCC option here. Then it sort of does some stuff based on that. You could do a lot of stuff here if you wanted to. GCC then passes the file, whatever front end is, does its stuff. And Gimple at this point runs all its passes. They're lowering passes, which are just to kind of improve the Gimple and do various things. Runs all the optimization passes, but each optimization pass has been replaced with this do nothing pass, which calls into the plugin and does nothing. And it does it very fast. Okay, and then at some point after all GCC optimization passes run, CodeGen passes run, and instead of generating registered transfer language, it just calls into here and bitcode is generated into an LLVM module. At this point, all passes have been run. At this point, GCC likes to output lots of stuff. Global variables, ident string, all kinds of mysterious things, which is kind of a problem because it's all going to end up in your assembler file causing all kinds of trouble. Except that I didn't mention this right at the start. I simply redirect all GCC output to /dev/null. So it's just all thrown away. I can't stop GCC producing stuff. By replacing the CodeGen pass with my own, it doesn't produce anything for functions, which are the bulk, but it does still produce bits and pieces of rubbish, and they just get thrown away. And then the compilation unit is finished. At this point, you have a callback, and that's the moment all LLVM optimizers are run, followed optionally by generating assembler code through the LLVM CodeGen. And then finally, everything's finished, and we finalize everything, print out some statistics if you ask for it, and that's it. So there were two parts in this plugin. One was redesigning LLVM-gcc so it worked as a plugin, according to the scheme I just showed you, and also the fact that it works with a much newer version of GCC where there have been a lot of changes. There were two major issues. One is that by the time the Gimple hits the Gimple to LLVM converter pass, the Gimple is in SSA form. It's got finodes and mysterious SSA names and things like this, and so it needed to be able to handle that. And the strategy was simply to convert directly into finodes and so forth in LLVM. And the intermediate representations, Gimple intermediate representation, got a whole new data structure. It used to be the so-called trees thing. It was just like a restricted subset of the possible trees, but now it's like a whole new set of data structures, so I had to sort of port the LLVM-gcc code to that. Let me explain about SSA form. You've got the function. Depending on the value of b, you either return x or y. Okay? So in LLVM-gcc, everything is done through memory. This is before it hits the optimizers. Once it's hit the optimizers, this all gets turned into a sort of one-line statement, and everything's much nicer. So this is the input to the LLVM optimizers, llvm-gcc. Everything's done through memory. The value of B is stored in some memory address. You load it out. You compare with 0. Depending on the value, you either come here or here. Here you load out the value of variable x and store it to a temporary. Here you load out the value of y, store it to the same temporary. And finally, everything branches to here, and you load out the value of the temporary, and that value of the temporary is either x or y, depending upon the value of b. This hits the LLVM optimizers, which turn into a nice SSA form and then simplify it dramatically. In the plugin, it's immediately the output to this kind of SSA form. This is what you get. There's no going in and out of memory all the time. GCC likes to add these numbers all the time to identifiers and things. So this is the value of the parameter b. It's already like a register. Depending on the condition, you either jump here or here. These blocks, they don't do anything. They just jump here. And here you have a fine node that, depending on where you came from, either uses x or y. So this is what, in the plugin, this is what hits LLVM. It's not clear whether it's better to do this SSA form in GCC and then convert to LLVM, or first convert to LLVM and then let the LLVM do this kind of form. But since in GCC it already is in this form, you might as well just push it across. This tuples representation is this new data structure. Consider an assignment. Z is sum of x and y. In LLVM-gcc, it uses this very fat trees representation. You've got a modify expression, that's for assignment. You've got your argument Z is some sort of tree structure here. You've got x and y, and you've got a plus expression. And in 4.5, you have a much more compact representation where you have a Gimple assignment operation which incorporates in it the fact you're doing an addition. And then you've got these guys, which are actually still trees. But this operation itself is itself no longer a tree. These trees, they use up a lot of memory. So in theory, there should be a lot less memory being used here, but my benchmarks didn't actually show any particular improvement. So I had to port the entire LLVM-gcc logic to deal with this kind of data structure. If you want to get it, you can check it out from LLVM Subversion repository. It's the same place as for LLVM. You just replace LLVM with GCC-plugin. Check it out. It's got a really horrible build system, but it kind of works, you know. So there's a little file which explains how to build it. It's pretty early days, but it kind of works. And if you've got any questions, ask away.